Questions 4.1 and 4.2 are the introduction to polynomials and some laws of exponents that we're going to need to have down pat. So this might be new, this might be a little review, this might be more review. It depends on where you're at in your 8th grade class. All right, so we're going to discuss some terminology, we're going to simplify by adding and subtracting, and then we're going to use laws of exponents. Some terminology. First, so you're going to jot these things down. I'm not going to write everything down for definitions. I'll write an example in the box. But you should jot things down that you need help with. What would we write down as a constant? What's a constant mean in math when you hear the term constant?
It's like the coefficient, like no matter what the x or y or any variable value is, it doesn't change.
Yeah, so it doesn't have to be a coefficient, by the way. It could be a number by itself, but a constant does not have a variable in it. So a constant, you would say, is the number, simply put. A constant is just a number. Easy way to define it. Now, a number could be defined like you could have ax squared plus bx plus c, and a, b, and c are constant integers. We just don't know what they are, but they're not like x and y, the independent or dependent variables. All right? So as Niall said, they could be coefficients. They could be just numbers at the end. All right, so for example here, oops. Let me zoom in a little bit so you can see a little better. Hold on. For example here, for a constant, if we had a function f of x equals 2x squared plus 3x minus 7, 2, 3, and 7 are all constants. 2 and 3, we're going to see in a moment, are called coefficients, and the negative 7 at the end there is just a constant by itself. Okay, but the constants in this problem are 2, 3, and negative 7. Those would be your constants in this one. All right. Next, the next term is a monomial. When you hear the word monomial, what does that stand for? What's that prefix really mean, Mike?
It's like one number shape.
Yeah, it's like one something, right? And omial usually has to do with polynomial, binomial, monomial. So it has to do with the amount of terms in the expression. So when you hear monomial, it means it has one term. Okay? Again, you can write this down if you want to put a full definition. A constant, a variable, or a product of those with, again, only one term. Only one term. For example, a number like 5 is a monomial. Or something like 3x squared y is a monomial. There's actually only one term. There are 3 factors there. 3x and y are all factors, but the quantity or the expression 3x squared y is one term. All right? Or something like, 4u. That's still one term. All right, those are all examples of monomials right there in the second line. Next, coefficient. Coefficient. What's the definition you could use for coefficient? How would you put that?
The number that comes before the variable.
Yeah, the number that's in front of or before the variable or attached to the variable. Okay, we can define it as like a factor in the monomial. A factor in the monomial would be the coefficient. So the 2 in 2x squared here, underline it, okay, is the coefficient. And you know that one for sure. We've heard that term many times. All right, so coefficient. Now, please remember, for coefficients, you could have variable coefficients. So when we start looking at the quadratic formula and we look at quadratics, we're going to use the general function ax squared plus bx plus c, or how about linear functions? Remember y equals mx plus b. M is a coefficient, right? The slope is a coefficient. So if I were to write it like this, just to give you a little outside look at it, if I were to write f of x equals mx plus b, m is definitely the coefficient, although it doesn't look like a number here. So sometimes when you understand the function, you're able to understand that some of the what look like variables are actually coefficients or constants. Like m is a constant. It's the slope of the line. All right, so although this looks like a letter, and you want to think, oh, that's a variable, it's really a constant coefficient, m. Okay, because m takes on a numerical value. And we know that because of the context of the problem. So you have to use common sense there more than looking and say, oh, that's a letter, so it can't be a constant. It is. M is definitely a constant. Okay? It's a constant coefficient. Okay? Coefficient. Next, like terms. What are like terms? What does like terms mean, Ben? When you hear the term like terms?
Like the same.
The same what? You're right. Give me more.
Numbers or variables.
Yeah, the same, really variables. The numbers can differ. So give me an example of two things that you could add together that would be like terms, Ben.
So 2x and 3x.
Yeah. 2x plus 3x are like terms, and it comes about because of the variable portion. Okay? So like terms are monomials that only differ in their coefficient. Again, look at this problem or this example. They're monomials that only differ in their coefficient. The 2 and the 3 are different, but the x's are definitely the same. Right? 2x plus 3x gives me 5x. I know I can do that because they are like terms. So again, like terms only differ in their coefficient. The variable part are the same. I mean, you could also have like terms like this, right? You could also have another 3x at the end. So in this case, the coefficients aren't even different. They're identical, but they're still like terms. So the key is that you have the same, oops, I should have underlined that differently. The key is that you have the same variable portion, okay, of each monomial. The same variable portion of each monomial. Question so far? We good? Polynomial? Polynomial?
2 terms?
Poly means
2.
or?
Like many?
Yes, 2 or more. 2 means really binomial. So polynomial, traditionally in math, is 3 or more, but poly really means many, so it could be 2 or more. But if you have something with 2 terms, let's call it a binomial. Okay, a binomial, and that's not even one of our definitions, but it's something we kind of should know from monomial, and then binomial means 2. Trinomial means 3, but once you get to 3, traditionally you start with poly. All right, poly means many, so something with more than one, okay, more than one term. So for example, x squared plus 2x minus 3xy. That would be a trinomial in this case, in more than one variable x and y. All right, a trinomial, and a trinomial is a specific type of polynomial. So for your definition of polynomial, okay, it's 2 or more terms. 2 or more terms. Or 2 or more monomial terms, if you want to be specific. All right, so that was polynomial. Next up is going to be the degree of a variable. What is the degree of a variable? See? The exponent. Okay, the exponent. So let's take a look at this one. The degree of a variable, for example, if we had 2x to the third, y to the fifth, what's the degree of x? The degree of x? And y? 5. Okay, so the degree of a variable, again, is the actual exponent, the number of times you multiply it by itself. It'd be x times x times x times y times y times y times y times y, the number of times. That's the degree of a specific variable. What about the degree of a monomial? Anybody seen this before? Of a monomial, such as this one. So here, again, x, its degree is 3, y's degree is 5. But if I wanted the degree of this entire thing, same example. What would the degree of an entire thing be?
Isn't it like the greatest exponent?
It's not the greatest. That's something else you're thinking of. We're going to get to in a moment. It's the sum of them. Hold off on your thought for the next one. So the degree of a monomial is the sum of the exponents. Okay, so this case would be 3 plus 5, giving you 8. All right, again, the degree of a monomial. Is the sum. Now, go back to what Kelly was mentioning a moment ago. The degree of a polynomial for the last example, so we have to have a better example than just this. So let me start with this again. And then I'll make it a polynomial by adding another term to it. Now, the degree of this polynomial is the greatest degree of the monomials you see. So what's the degree of the first monomial over here that we had from a moment ago? This degree is? Okay, and what would the degree of this one be? 11. So the degree of the polynomial itself would be 11. Okay, so that's where the greatest part comes into play. This is just nomenclature, just being able to use these terms. All right, so when you're speaking in mathematics, you understand what you're talking about. So the degree of a simple variable is just its exponent. The degree of a monomial is the sum of the degrees. The degree of a polynomial is the biggest degree of the monomials after you figure them out. All right, usually you write a polynomial in decreasing degree. So that's why you usually see x squared plus 2x plus 5. What's the degree of a constant? What is the degree of a constant?
1.
It's not. I know you would think it is, right? If I have a constant like the number 5, remember the degree comes from the variable portion. What's the variable there though? If I have the number 5 right here and I put an x next to it, well, that's not true if I wanted to keep it 5. What do I have to make the degree of that x so it doesn't really exist?
0.
0. Remember, and this is one of the rules we're going to go over in a minute, anything to the 0 power is really 1, right? So if I wanted to find the degree of the number 5, I need to think of it this way as 5x to the 0. So now you can clearly see that the degree of this is 0. Okay? So remember, when you're looking for the degree of a monomial, you have to look at the highest exponent of the variable portion. And since this variable portion is x to the 0, then the degree of a constant is indeed 0. Okay? Maybe that's a little note you want to jot down, that the degree of a constant is 0. Do these terms make sense? The vocabulary makes sense that we need to use here? All right, so let's take a look at this first example. Simplify and arrange terms in order of decreasing degree of x. And be careful here. It specifically says degree of x, not degree of the monomials or in decreasing degree of that. Then it says, then determine the degree of each polynomial. So in the first one, what are some of my like terms in the first one? What's a like term here? Well,
X to the second.
and
X.
negative x to the second, and where's the other like term from it?
4x to the second.
Yeah, there you go. So those two are like terms for sure. And it looks to me like those are the highest degree of x, right? They're x squared, so start with those. Yeah, Mike?
3x and 5x.
3x in the beginning, and the negative 5x at the end. Very good. And then the last two things that are left are both constants, right? So those are like terms as well. So let's start with the green first. So we've got negative x squared plus 4x squared. Well, that gives me 3x squared. Then I go to the red and I see I have a positive 3x minus 5x, giving me a negative 2x. And then I go to my constants, I see I have a negative 9 and a positive 2, making this negative 7. All right, does that make sense how we do this? Simple, okay, but just something that we have to be able to do. It's in decreasing degree of x. In decreasing degree of x. What would the degree of the polynomial be? What's the degree of the polynomial? Remember, you look at each individual monomial, find the degree of each, and then the highest of them is your polynomial's degree. Niall?
3.
Not 3.
2.
2. Look at the degree.
Oh my God.
Remember, the degree of this is 2. The degree of this is 1. The degree of this is 0. And a polynomial's degree is always the largest of the 3.
Yeah, my bad.
You looked at the coefficient on that part, yeah. Okay, so again, make sure you look for the highest exponent. Right? Highest exponent. So decreasing degree of x. All right, how about part B? How about part B? Give me some like terms for part B. Some like terms to start. Give me one of the like terms.
Negative 8x y to the 4th power and 2x y to the 4th power.
All right, so we see that those are most definitely like terms because the variable portions are identical. It's the coefficients that differ in this problem. What's another set of like terms? I definitely see one more set of like terms here. Ben?
5x to the third, y to the third, and negative x to the third, and y to the
Very good. Okay, and that looks like that's all I've got for like terms. The other part is not like terms because it's x to the fourth, and I don't see that anywhere else. Now the question becomes, how do I arrange this in order of decreasing degree of x? Decreasing degree of x. What's the highest degree of x in this problem? What's the highest degree of x, Luca?
2x to the 4th y.
Yeah. So I'm going to start with this term right here. All right? I'm going to start by writing that one first. And there's no like terms for that, so it leaves it alone by itself. And that's the highest degree of x. What's the next highest degree of x? The green part, the red part, or the first part that we didn't really underline? Because we have sums of terms here, obviously. Kelly?
The green part?
Yeah. So take a look at what's underlined in green. That's x to the third in both cases. So I've got a 5x to the third, y to the third, and a negative x to the third, y to the third. All right? Now, so I've got an x to the fourth. There's x to the third. Do I see x squared anywhere? Where's x squared in this one?
First term.
The first term. And it's got no like term, so I just write it by itself. And then finally, last but not least, must be the remainder, right? In red. So I'm going to have a negative 8xy to the fourth plus 2xy to the fourth. All right? So I've listed everything in decreasing degree of x. And now I'm just going to simplify my like terms. So this remains. In green, I've got a positive 5. Remember how to add like terms. You wouldn't believe how many people forget how to add like terms. Just look at the coefficients. This is 5. This is a negative 1 right here. 5 minus 1 is 4. Okay, so this is just a plus 4. X to the third, y to the third. Remember, it's like you're adding apples and oranges. You can't add 5 apples to 6 oranges and come up with 11 apples or 11 oranges. You'd have to have a different category like fruit. Here, it's 5 apples minus 1 apple. So you don't change the amount of, or the name apple afterward. X to the third, y to the third remains itself. I carry down the next part because there's no like terms. And then finally the last part, I've got negative 8 and a positive 2 giving me negative 6. And then I carry over the variable portion. All right, so this is my polynomial in decreasing degree. Now, the question though at the end said, what is the degree of the whole polynomial? What's the degree of this polynomial? What's the degree of this polynomial? And find the degree of each part individually if you're forgetting how to do this. Answer, anybody. For this one, the first one on the left, what's the degree?
4.
5. You have the y there, don't forget the y. How about this one?
6.
This one?
4.
And this one?
5.
All right? So again, we're literally adding the exponents together for each of these individually and then circling the one that's the biggest. All right? So the degree of this polynomial is 6. All right? But it is decreasing in degree of x. In degree of x. X to the fourth, x to the third, x to the second, and x to the first. Can we move on? Any questions on this? Pretty straightforward so far? How many people are like, this is brand new to me, completely brand new? Okay. Good to know. We're going to perform indicated operations such as sums and differences. So part A you can do on your own. Go ahead and do part A. Find the sum of those polynomials. Find the sum of those polynomials. And again, if you'd like to use underlining, you can underline, that's fine. Nick. Thank you. You're right. A to A. So I've underlined them in colors. Feel free to do whatever you like, just to add them together. If we're trying to find the sum of these, I would start with the highest degree. And I see the highest degree is 4x to the third. And that has no like terms, so I can leave that alone. That part doesn't really matter. Then I go to the x squared terms, and I have a negative 3x squared and a positive 5x squared. Okay, that'll yield just simply 2x squared down here. Then I go to the next term, which is linear. I've got a positive 2x minus 6x is going to give me a negative 4x. And then last but not least, I've got a positive 4 and a negative 5, giving me a negative 1. Alright, so again, you don't need to do this. You don't have to show every step, please. There's no reason for you to show this intermediate step. I'm just doing this so you can see. Did I make a mistake? It probably is. I made a mistake. Where are we at? Yes, thank you. So the second term should be a positive 2x squared. Thank you. Again, please, you don't need to show the steps along the way. Alright, you can definitely do something like this in your head. There's no reason to show steps. How about for part B when you're finding the difference? Find the difference between. When you hear the difference between, what do you think right away? Subtract. Now, how do you subtract though? Which from which? How do you remember how to do that?
You just do it by adding the negatives. You break it. With the first one, you leave it alone, and with the second one, parentheses, and multiply by negative 1.
Yeah, so let's do that. Let's take the first one. We're doing this entire thing minus the entire second one. And as Luca mentioned, when you think of minus, think of adding the opposites of each. All right? So literally switch all these signs on the right-hand side and combine like terms. So we'd end up with just simply thinking about it this way. Okay, again, I'm showing you all these steps. Please, there's really no need to do every single step. Okay? But I literally switched all of these signs on the right-hand side. And then just combine your like terms as we did in the last example. 6y cubed minus 2y cubed is 4y cubed. There's only this negative y squared by itself over here, so I'm going to write that by itself. Then I'm going to see that I've got 2y and 1y giving me 3y, and then a negative 5 and a negative 2 giving me negative 7. Okay, so again, like terms, and then finally the constants are also like terms. All right? Any questions on combining things like this? You're looking for the same variable part and you're just adding the coefficients. All right? Please, do me a favor. Don't make mistakes on this kind of stuff on a test. Be careful. Check your work. It's going to really upset me when something's simple like this, if you make a mistake on it because you're thinking about multiplying and stuff. All right? When we get to multiplication, you're going to have several rules at once. So don't forget how to do something as simple as this because you've learned something new. Which means you got to make sure you just practice simple stuff too. All right, simplify. So how would you go about simplifying something like this? Niall? Distribute to start. All right, when I distribute the first term, what do I get?
4yx minus 6x.
All right, good. Second term, Ben. Distribute the second term for us. What do I get when I distribute this?
4x plus 2y.
And the third term, Will, go for it.
Negative 3yx and 6.
Positive or negative 6?
Positive.
Good. Remember that this is a negative 3 times a negative 2, giving you a positive 6 there. All right. So as a result, we can then go ahead and look for our like terms. It looks like I've got a 4yx and a negative 3yx. 4 minus 3 is simply 1. So I've got 1yx. Next, I've got a negative 6x and a positive 4x. Negative 6 and 4 gives me negative 2x. And then finally, 2y and 6y over here gives me 8y. All right, yx minus 2x plus 8y. I know I'm going through these quickly, but it's just because they're simple, quick problems. All right, please ask if it doesn't make sense. So we distributed, and then we looked for and identified like terms, and then we combined the like terms in the problem. All right? Let's go to example 4, which says the following. Determine the values of a, b, and c that make the equation true. And at first, it looks like this is a bunch of gibberish because a is in many locations, b is in locations, c is on the right-hand side. you're going to be wondering what is actually happening. So my recommendation is that you try to simplify first. So why don't you simplify the left-hand side of this? Please don't subtract things from one side to the other. It won't help you. Okay? Simplify the left-hand side of the equation. Simplify the left-hand side of the equation. So it's easy to start simplifying. What's x squared plus another x squared going to give you? Yeah, 2x squareds. And on the right-hand side, I still have cx squared. Okay? So keep this correlation in the back of your mind. Next, let's go to the middle term. That just has an x as a variable. I see ax and a negative 2bx. How do I add those together? How do I add? I'll underline them in green. This is definitely a like term with this, although it doesn't look like it at first. Remember that a, b, and c are coefficients. How could I write them together as one term? How could I write that? What if a and b were numbers? If a was like 7 and b was 2. And if a was 7 and b was 2, hypothetically, you'd have a 7x, right? You'd have a 7x right here. And if b was 2, this would be a negative 8x, right? And you could combine them by simply adding these two terms. So since they're not numbers, though, they're not numbers, how can I think about them? Luca.
Do it like ax minus 2bx, and then x's that cancel out, you a minus 2b.
You're so close. You made one mistake in your statement. You made one little mistake. So he's right. So start by grouping them like this. The x doesn't cancel out, though. The x does not cancel out. What's the correct word or the correct way to say it? Because that's what I've got. I've got an ax and a negative 2bx, and they definitely have the same variable part, right? That x there and that x there are the same, so they're like terms. What could I do to write these a little bit nicer so that it looks like a coefficient and one coefficient only?
Well, I don't know, minus 2a plus b x squared.
Not x squared. Okay, I see what you're getting at there. Only if you're multiplying x times x do you ever get x squared. So there's no x squared in this problem.
Did you factor x out?
Yeah, you could factor x out of those and put them separately. Watch, if I put an x here and write it like this. Take a look at what that looks like. See if it makes sense. If you were to distribute that back out, distribute the x to both terms, you would get ax, and then the next term you get negative 2bx. So again, I'm not going to do it, but I'm going to show you physically. Ready? If you were to distribute this to both terms, you would get back to the previous line. So you're factoring x out, but I'm writing x on the right side to show that this is the coefficient over here. Okay, so you're really factoring the x out of this. How about the last part? The last part I have 2b and 3a. Well, those are definitely not like terms, right? But they're both constants at least. If a and b are numbers, right? A and b are numbers. We're trying to find the values of them. So if they're both constants and they're both numbers, then I can at least think of them as one entity. So I might just, in my mind, do this. Just group them in your mind. All right? Now again, this is equal to the right-hand side of the equation, which says cx squared minus 7x plus 3. So look at this whole thing now. Okay, read this entire thing to yourself. Think about it. This 2 is in front of x squared. Well, what's in front of x squared on the other side of the equation? So what does that mean to you?
You can factor out x squared.
Not factor out. Just think about properties of equations. If there's an equal sign, it means that this term must equal this term. This term must equal this whole term. This 3 at the end must equal this whole term. So what could I do, right? C is equal to 2. Just look at each side of the equation. It's called vector analysis. There's a fancy term for it, but just make common sense. Find x squared on both sides. The coefficient here is 2. The coefficient here is c. Thus, c must be 2, really. For this statement to be true, the only way this can be true is if c is 2. In a moment, we'll figure out what a and b are to make that a negative 7. and then we'll figure out what A and B are that makes that a positive 3. All right, but we can clearly see that C is taking the place of the number 2 on the left-hand side. So I can do this. I could say to myself, these are the same. All right, so C is equal to 2 as a result. Right.
Does that mean you can cancel those two out?
It's like you're canceling them out mentally, sure. But we're not really solving an equation. We're just coming up with A, B, and C. So there's no need to cancel them. But next what we can do is just forget about them. All right, let's go to the next thing now. Go to the next thing. Where's my X term? My X term on the left-hand side is this whole thing, right? And then my X term on the right-hand side is this piece right here. So I could set these coefficients equal to each other. So I could say that A minus 2B, right, this coefficient has to be equal to whatever's over here. Well, what's the coefficient over here?
-7.
-7. So again, I'm looking at my terms and I'm saying the degree of this is 1, the degree of this is 1, therefore those coefficients must equal each other. So I set them equal, which looks like it helps us, but not much just yet. And then what's my constant on the right-hand side? What's my only constant that's by itself over here without a variable term? Ben? 3. And this is by itself, isn't it? Do you see an x next to it anywhere? So that must equal 3. So this whole portion here is equal to that 3. So my third equation I get is 2b plus 3a equals 3. So it looks like I've got 3 equations, one of which is known, so this one's done. We don't have to solve it. So I could solve this one as a system, either using a matrix, if I realign this, mix up these two, so that it's aligned with A and then B and then a number. You can use a matrix or whatever. You'll get A is -1, and you'll get B equal to 3. All right, so those would be your 3 answers for that one. The second part of this is from 4.2 in your text, all right? And they're just properties of exponents. I'm going to make the assumption that nobody knows these, when in reality I know that a lot of you do recall these properties. All right, so for example, the first one, the property of products of powers. How can you explain that that's true, that statement up there? Can you give me an example that explains the reasoning behind that? Paul? Base, yeah, same base, you can add the what? Yeah, so give me an example, Paul.
X to the second plus x to the third.
Times? Times, right? Product. So what do you get as a result?
X to the sixth.
And if you want to check that it's true, obviously, you could literally list them. You could say x to the second is x times x, x to the fourth is x times x times x times x, giving you 6 x's, therefore x to the 6th. Make sense? Seems trivial. Okay, this seems very trivial, and it is really, once you get it down pat. But I can't emphasize how many mistakes I see on tests all the time with the properties of exponents and rules. Instead of, adding them together, I'll get answer of like x to the 8th, where somebody multiplied 4 times 2. All right, so you need to know these. And if you ever forget them, just derive them in your head. Think about what it physically means. Anybody know how to prove the 0 exponent rule? Not even a proof really, but an example of to show how anything to the 0 is really 1.
So it's so for a to the 0, it's a 0 times. So whenever there's like nothing there, it's just a 1.
All right, I see your understanding, but give me an example more than. Give me an example of how you prove it. For example, what's 2 to the 4th? 16, right? 2 times 2 times 2 times 2. What's 2 to the 3rd? I should write it over here. It'll make more sense. What's 2 to the 3rd? Anybody? You did 2 times 2 times 3. 2 times 2 times 2, 8. What's 2 to the 2nd? What's 2 to the 1st? So look at the answers on the right-hand side. What are they all reducing by a factor of 2, aren't they? Aren't you just dividing by 2 every time? So when you divide 2 by 2, what do you get? 1. Well, what's the next in line? It's to the 0 power. Okay, it's a simple reasoning. You can do this with any number to see that. Okay, so going from each line successively, you're dividing by 2. So anything to the 0 is going to give you 1. And you could try this with any number. Try it with 3. 3 to the 4th is 81. 3 to the 3rd is 27. 3 to the 2nd is 9. 3 to the 1st is 3. 3 to the 0 is 1. Okay, anything to the 0 is always 1. Anything but 0, yeah, that's a good point. You're absolutely right. Anything but 0. 0 to any power is 0. 0 to any power is 0. I mean, that's obvious because like 0 to the second power would be 0 times 0, which is 0. Okay? A power is really, remember, writing out how many factors you have. Like x to the 5th is x, 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 x. So anytime there's a 0 there, it's a factor. So it's going to be 0 automatically. Number 3, who can explain number 3? Again, I know that maybe there might be some of these new, but I want you to explain them. Not just understand them, but explain them. How come a to the b to the c is a to the bc? Luca. You're what? Okay, be careful with that word. I know you like to use the word distribute, but distributive property specifically refers to when there's an addition operation and multiplication. But give me an example or reasoning to why this works. Okay. Give me an example. Pick some numbers or pick a variable and some exponents. Make it easy for yourself. 2, 3, 5. So I'm going to go with x to the 2nd to the 3rd. I don't need the 5. So give me an example of why this is true, why it works. Okay, but why is that true? I want you to explain it. I don't want you to give me the answer. I'm trying to ask you to explain it. What's x to the 2nd to the 3rd really written as? How could you rewrite that? Sabine? Yeah. That's what I'm saying, Lucas. So explain it like this, okay? It's a little more obvious now. So x to the 2nd to the 3rd really means take the quantity x to the 2nd, write it 3 times as factors. That's what to the 3rd power really means. And then if we go back to rule 1, we can see that this becomes 2 plus 2 plus 2, which is really 6, right? Which is really x to the 6th. So to make it easier, just multiply these two quantities and you skip that middle step. All right? That's what I meant by explain. Number 4, the power of a product. And this is closer to distributive than the last one, really. Okay? Even though it's really not called distributive, so let's keep that in mind. Charles?
So if there's I think it's a coefficient, if it's not 1, then you have to distribute.
So like this, right? Like this, Charles?
So 2x to the 5th, it would be 2x times 2x times 2x 5 times.
Yeah, very good.
So the coefficient changes also.
Yeah, so notice the coefficient repeats itself 5 times. So in reality, you're taking this 2 here. Focus, guys. You should all be looking up. Some of you look off into space. Focus. This is really 2 times 2 times 2 times 2 times 2. That's what this means. So you need to, as Luca mentioned a minute ago, it's like you're distributing the power. Okay, it's like you're distributing the 5 to both factors, to all factors. So in reality, this is really 2 to the 5th times x to the 5th, which we can write as 32x to the 5th. All right? It's the same answer you get by using it this way, but you don't want to do all that work. So you're learning shortcuts really, okay? You're learning rules to make life easier on you. Does that make sense, the idea behind these? Okay? Any other questions on this? Can we do an example? So let's look at example A to start. A to the 2nd to the k times a to the k to the 3rd. Work on them individually. Think about this piece first, and then think about that piece. When you raise a power to a power, what was your rule? What do you do to those powers? What, not? Multiply. So what's 2 times k? How do I write that? 2k. Again, how do I write 2 times k? I write it as 2k. What's k times 3? 3k. All right, so I've written it like that, which makes life easier on me, doesn't it? And now what do I know?
And then you can add them, so it's a and 5k.
Very good. I add the 2k and the 3k together to give me 5k. All right, so I notice, as Paul mentioned earlier, The base is the same. The base is a. A to the 2k times a to the 3k means you add 2k and 3k to get 5k. How about the right-hand side now? A little bit trickier. A little bit trickier. What do I have to start by doing? What do I notice? I've got a factor out front and then a binomial in the middle. So I have to do what with that factor? Distribute it. To start by doing this. All right, distribute that to both terms. So here's what I have now. So I've distributed it to both of those terms. There's still a plus sign in the middle in red right here. And there's that plus sign. But I've distributed it. And I'm just writing it separately. I'm not actually multiplying yet. So x to the m minus n times x to the m plus n. What does that become? What does this become over here? The product of these two, right? X to the 2m. Yeah, I couldn't hear you. 2m. Because what happens to the n's, right? Yeah, remember, when you multiply things, you're adding the exponents. So this becomes x to the m minus n plus m plus n. You add those exponents when you multiply things with the same base. So the n's cancel, leaving behind x to the 2m. How about this right-hand side over here? Paul, help me out over here. If I'm multiplying two things with the same base, what do I do to the exponents? Say again? Not times 2. You told me this one before, Paul. Go back over here, look. When I had this situation, what did I do to the exponents? Didn't I, right? So aren't these bases the same? So what should I do to the exponents? Alright, so I have this plus n, right? Like that? That's what I've got? And what does that result in? Yeah, just m. Why is the n? What happens to n? Yeah, the n goes away. The negative n and the positive n goes away there. Now, can I simplify any further? Can I simplify any further? I can? What do you get? It's a common mistake now. There's not a time sign here, right? This is not a time sign. You can't add the exponents. There's nothing you can do. Okay, you can't do anything there. Now, granted, you could probably factor something out. Is that what you're going to say? You could. There's no need to, but you want to display how to do it?
Let's just say x to the m power to the third power.
No.
If you factor it out, is that actually simplifying or is that just
No, it's just
the opposite?
in reality, all you're doing is manipulating or changing the value, changing the expression, but you're not actually simplifying by factoring something out. Sometimes it's useful to factor things out because they might cancel, but there's no denominator to cancel it. So there's no real need to go any further than this. Okay, there's absolutely no need to go further than what you have here. If you wanted to, though, here's what you could think of this as. Okay, you don't need to, but I'm just going to give you a little insight. You can think of it like this. Then technically there's x to the m in both terms, right? So I could write it like this. So that is also correct. See if I watch. If I distribute this back out, distribute this out. X to the m times x to the m. That's really x to the 2m, isn't it? And then x to the m times 1 is x to the m. So technically speaking, I could have written it this way and then factored out x to the m because it's in both. But these lines right here that I'm boxing in are not necessary, really. Okay, this is more than good. It's good to be able to simplify things, though. You should be able to use that technique of factoring stuff out. Okay? All right, let's stop there for this session.